Hi, my name is Skynelsonisaacs, and I'm here to talk today about the holographic time intervals theory that I've developed and worked on. And happy to be with SSE again, Society for Scientific Exploration. It's been a few years since I've been in touch with many of you. The subtitle is A Frequency Domain Framework for Quantum Evolution and the Emergence of Time. Ambitious. I'm excited about it. So, time intervals as whole entities are represented in the frequency domain. That's the goal I'm trying to reach today with you. To describe a time interval not as a piecemeal, gradual unfolding of the clock, but as a whole interval that cannot be subdivided without you noticing. This is the difference between reductionism and holism at its essence. So it starts with the observation that Lorentz transformations lead to light traveling along null intervals. In special relativity, according to Albert Einstein's theory and Minkowski's work with it as well. Lengths contract and times dilate until light intervals themselves become essentially null intervals or zero proper time. And so continuous motion is not well defined. Gilbert Lewis, the physicist and chemist in the 1920s, said light leaving the sun and hitting the earth is really in virtual contact. We're in virtual contact with the sun, meaning that the light itself doesn't actually evolve over time, even though there's 8 minutes of travel that we perceive. So this has to do with the different reference frames of light, which has an undefined reference frame at the speed of light, and ourselves. So we don't think about it as light not experiencing time, but I do like to say light does not register time. Light cannot change or register any kind of change in the physical world without, there's more to that I've written about before, but for today, just the idea that continuous motion is not well defined, only whole intervals. And that's the takeaway, that the distance from the Earth to the sun has to be thought of as a whole. So it's this essentially quantized, not in terms of Planck's constant, but in a sense of like discrete leaps of travel. And the same applies for anything traveling across space, through from Andromeda Galaxy. It's a leap from a point that was in the past to the present when we look at Andromeda's light. But it didn't travel continuously along the journey. We have to think of it as an update, uh, a discrete update in both location and time. So what does that lead us to, or how do we motivate that? And this is the Minkowski diagram that sort of gives you a sense of that. An observer traveling at a high speed on the left, at this angle of, small angle relative to the vertical axis, the time axis, it experiences events E and F slightly out of sync. They're simultaneous from one point of view. E and F are simultaneous along the same horizontal line, same time, but E prime and F prime are slightly offset, out of sync. As you get closer and closer to the speed of light, F prime becomes much, much earlier perceived than E prime. And so the farther events happen first. And this is part of the construction that leads to the timelessness of light itself. And also, just a side note, current theory I have for how time flows has to do with this Lorentz contraction, but I'm sure we'll come to that maybe at the end. So what I want you to have in your mind here is a really compelling image for me of pixels versus patterns. You can create an image of the city using pixels, obviously. That's the reductionist model, side by side pixels of light. Or you can use patterns, which take up the whole space. Each pattern takes up the whole space. If you have enough patterns together, you can create an interference pattern, which gives rise to the image. And that image has the same amount of data, same amount of say 60,000 patterns rather than 60,000 pixels. But it's a very different way of creating the image, a holistic way. And you can see this example here. On the left, you have the dots in the frequency space showing you the intensity of each frequency in the spatial picture, basically telling you how grays and whites vary over space. And the center is zero frequency, and going outward is increased in Y and X frequency. But if you filter this by removing the high frequencies, you get rid of the edges, you blur it, because high frequencies correspond to quick variation in color and space. And I can remove more high frequencies and I get more blur. And then the lowest frequencies just correspond to the really gradual changes over space. Um, so we can also remove the low frequencies and have a high frequency filter, and we keep the edges. So what we're doing is identifying the nature of the whole image at once using this pattern-based approach rather than looking at every single point on the pixel on the image and saying, does this have an edge or not? So there's this holistic or holographic, it is the same mathematics as holograms, way of looking at space, which I think is really important. And as we layer more information on in the form of patterns, get more resolution in the whole picture. This idea, both in sound and time domain and in space image domain, helped inspire my thoughts on these matters many years ago. So the first piece, that foundational piece I want to put in here, parameters versus coordinates. So we're going to propagate signals via the Fourier transform. And the Fourier transform is what converted between those two domains in the last picture. So the consequence of this is that motion emerges as discrete updates, not continuous, which is what I said a minute ago from the Lorentz transformation, which I didn't prove to you, but it is straightforward result from the null interval idea. Parameters versus coordinates. So if you think about it in the Schrodinger equation, for instance, and in any kind of integral equation, you have a parameter that you integrate over, right? In the Schrodinger equation, it might be time or position. You also have, but that integration parameter has no definite value, right? It's from negative infinity to positive infinity. So it's not really a thing. It's not measurable. I call that a parameter. And the coordinates are actually different in their nature. They are, hi dog. They are discrete or finite. They've got a certain position to them, a certain location. They're definite. So this is a very important distinction in the Fourier transform because when you convert between a spatial or temporal representation on one hand and a frequency-based representation on the other hand, the parameters go away. You go from a spatial temporal parameter to a frequency parameter, like energy momentum parameter. But the coordinates, the finite values of where something actually is in space or time, they remain. And the frequencies, sorry, the positions in space or time become frequencies of oscillation in the spectrum of an object in the frequency domain. So it's very beautiful how the frequencies in one domain become coordinates in another, coordinates in one domain become frequencies in another. And this is a really important foundational piece of the mechanics that I think we can use to derive wave function propagation. So what does that look like? So inspired by Fourier optics, you have waves coming in, plane waves coming into an image from a light bulb or a laser, hitting an aperture. This is a cutout of some kind of aperture picture, creating a waveform that's complicated after that and moving to the right. At the top, we have the transmission function, I think, the TA, the signals coming initial and put through. H is the impulse response function, which is how the signal travels in space and arrives at the screen in some certain form. We call that GF. If you do this in the frequency domain, what you find is, and this is typical how it's done, you have I mean, that's what's happening here. You create the waveform from the image from the aperture. You evolve it in the frequency domain by changing the phases of each component of frequency. And so the frequency components evolve, and at the final point when they interact, you haven't moved them in space, but you've evolved the phases, and they update to a different position in space. So time evolution and space evolution really have to do with just updating phases across the whole waveform, the whole spectrum. And the same process is exactly the same in quantum wave functions. You just replace the light wave with a quantum wave function. This is the transfer function H, capital H. Okay, so this is all in the spatial domain or temporal domain on the left. In between the pictures is the frequency domain. Now, that inspires the idea of converting to this frequency domain. And you can see how this is a discrete update. It goes from being in space-time on one hand to being suddenly evolved to a screen without necessarily crossing the space in between unless you put a screen there. There's no assumption of that. continual motion. And this is what I was saying about coordinates becoming frequencies in the dual space. Wave function psi1 is made from some amplitude function x of t, x and t, and some phase factor, oops, e to the I k naught x minus x naught. That's k naught is an actual frequency, an actual value that we can measure. X is a parameter, so it's not a value, it's just a variable. X naught is an actual value, so that's a position in space of this wave function, x naught, or this component, this wave function. So the same goes for omega naught and t naught. They're coordinates, they're actual measurable numbers, whereas t is a parameter, which is integrated away. And when you take the Fourier transform, t and x disappear, you get k and k naught. And so you have phi, the frequency domain function, equals a of this function k minus k naught, an offset parameter, offset by the coordinate that you started with. And the important part here is e to the phase factor. You have k minus k naught, which is an offset by the finite frequency of this particular component, or this particular situation, and the energy, the momentum of that particular object. And k x naught is the actual position it was in when you last, when in the spatial domain. That is not a part of the variables there. So the bottom equation is not in the spatial domain, it's in the frequency domain. And x naught and t naught are the frequencies corresponding to the spatial frequencies corresponding to the way that the spectrum changes over frequency. So k is a variable and x naught is the frequency. Omega is a variable and t naught is the frequency. If you understand what I'm saying. Spatial frequencies are analogous to regular frequencies in the other domain. So it's pretty beautiful how it works. We'll just skip that slide for now. This has to do with visualizing the actual displacement and the speed in physical space as variations in frequency domain. So two distinct notions of time emerge from this: parameters versus coordinates. Parameters have a hidden order, or I hate that word, but they are implicate in the sense of not being measurable. They don't correspond to measurable things. Coordinates are measurable outcomes that we actually experience and can say exist, explicate. The key insight here is that reality is structured holographically. Parameters encode a timeless whole and govern the evolution of the system. The tides and the atoms oscillating in their molecules and all the functions of nature evolve in a parametric way that we can't measure until we observe it, and then it becomes a coordinate that we say this is the time at which this thing happened. This relates to the measurement problem in a way, because you've got things are evolving, but according to the parameters, not according to any kind of measurable, definite outcome. So it gets really beautiful when you consider the holographic model, because this is really how holograms work. If you tilt a hologram to illustrate parameters versus coordinates, the parameters correspond to the hologram itself, the piece of film that you've got the interference pattern on. So you've got, I've overlaid a grid there in orange, you can see here, to show you the physical space of the actual film. And the buildings I just tried to mark. I didn't do a very good job because it's hard to get this to do with AI, and it's a hard graphic, but I'm trying to illustrate three different objects, A, B, and C, in the actual image that are not on the film, but they appear in the film. So these are located by coordinates A, B, and C. The grid in orange is illustrating the parameters on the actual film. And if you tilt that, you see the buildings move, and I didn't show you A, B, and C, but you can see all the buildings do shift relative to each other, right? There's a 3D adjustment left and right, which is the coordinates changing position, right? Because they're not, the film is still, it's changing it fixed relative to fixed, I say, not relative. The grid is the film parameters whose positions are fixed relative to each other. Yeah. The red boxes are buildings whose coordinates move relative to each other, right? This is the difference between the fixed coordinates, the fixed parameters, which are part of the unmeasurable holographic film itself, the thing itself, and the thing you're envisioning in there, which are objects that appear to be there and move relative to each other as coordinates. I wish I had more time to go into that, but hopefully that's a good intro. So next, getting towards the conclusion here, the spatial geometry of a system sort of corresponds to a frequency spectra. And my last paper this past year illustrates how when you divide a spatial geometry into pieces, like the light coming from the sun into two different chunks from the sun to Mercury and then the Mercury to the Earth, it changes the spectrum. So continuous motion or a whole interval is not the same as piecemeal, or piecemeal being like you can't just divide up the interval into infinitely small pieces and say it's the same thing. Why? Well, if you do a Fourier transform of, if you assume the world is this frequency domain duality is crucial to deriving quantum mechanics, which is true because you can derive the Schrodinger equation from it. I'll try to show you that. Then if you think about, if this is possible to think about the duration of time from the sun to the earth of that photon as this distance here, this time, and you take the Fourier transform of that, the spectrum you get is here, a real and imaginary part of the spectrum. You could take the amplitude of that if you want. But if you think of that as two separate distinct intervals, it's really the same thing, right? It's going from here to there and then there to there. But the Fourier transform of those two intervals is not the same as the entire thing all at once. So the representation of the frequency domain, and hence the spectrum that you get out of that signal, is going to be different. And that's because of what we call, I've got it in my notes, operator theory, where the fact that you've taken a Fourier transform introduces artifacts into the system. So got some notes here that I forgot to remove, but this leads to a few different things: stellar distances, quantum eavesdropping detection, and quantum computing, which we'll talk about. But the idea is that spectral distances are revealed by the signatures of the spectrum in there, which is pretty amazing. It means that we can measure the distance to the stars. And here's another example. You have a barrier with L at the top and then two half barriers in the middle. You can see that the spectrum itself is different. So you cannot add Fourier transforms. Finally, to get this idea that time intervals as whole entities in the frequency domain should be represented that way, we have the following. Time is defined relative to discrete events structured in the frequency domain. So from theory to testable phenomena, a beautiful way to think about this is attosecond laser pulses, which we already know to be possible, and we have a theory that describes them. But what we're not thinking about carefully is that these are not individual pulses that are just moving like bullets, like particles. They are an entire chain of a single object that's a waveform like the ocean. It's a standing wave it's not separate objects, and that's the way it's created in the lab. And we can't create individual points of photons. Create a chain, and this is exactly what comes out of the idea that the whole spatial boundaries, the beginning and the endpoint, matter to determine the spectrum, the photon, right? Because then it's not just the beginning creates the photon and then later you receive it. It's the entire interval is known at once, creating a frequency pattern for that whole system. This has some really profound effects. As I said, the Fourier distance mapping distance to stars using spectral artifacts from finite travel duration, you get something kind of like this, where you have introduction of artifacts in the spectrum due to the finite nature of that duration of travel, like a box, cutting off the signal in a box, and you create kind of like Gibbs function artifacts. And the frequency difference or distinct spread that you would get is approximately 10 to the minus 10 hertz. So it's very small, but it's at the limit of what we can detect now. So it's something we could actually use to measure. That's for a star Alpha Centauri, about 4 light years away. As you get farther away, this gets smaller resolution and it gets harder to test. But it is possible. And quantum eavesdropping tells us that any disturbance by somebody in the middle of the travel of the photon of the quantum particle would leave a signature, a spectral fingerprint marking the moment of interaction. You could tell when it happened and that it happened. So in short, time splits into parameters, unmeasurable, and coordinates, which are measurable. These are just two different concepts, both in the mathematics of quantum mechanics. And the Fourier transform shows whole histories encoded, outcomes projected. The whole history of the photon is known from not from the beginning, but as a result of the whole interval of time, the whole history. And so there's a way in which holistic time is very different from reductionist gradual time. And it's not acausal, but it's holistically causal or holographic. So we need to understand that a little better, a lot better. And the flow of time essentially emerges from a timeless backdrop. So these are the papers I'd encourage you to check out. I'd love to get your feedback on them and some blog posts that summarize them. And I'll just take a minute to continue with some mathematical notes for those of you who are interested in case there's time. The time-dependent Schrodinger equation can be rewritten in terms of this mathematics. You start with the psi of t prime is equal to the integral over some time interval of the time interval times with the Hamiltonian acting on the wave function. This can be rewritten as an integral over energies, or a sum over energies, and then a Fourier transform of that, the inverse Fourier transform of that, all nested within a Fourier transform of this function here, the rect and the potential. And we can talk about how this works, but it's all very straightforward when you look at it. V is the energy, the potential energy function, and rect is the function of this interval t naught to t prime. It's just a square function. And so when you do this, you can rewrite these as Fourier transforms of images, inverse transforms of functions themselves, get the Fourier transform of the inverse Fourier transform, and this becomes a convolution theorem, using the convolution theorem. So you get a sinc function in the frequency domain determined by the width of that function is determined by the time interval, delta t, convolved with the potential function, convolved with the original energy distribution itself, C, times these delta functions, which picks out the particular components, discrete components. And it's beautiful. What you're doing is essentially reconstructing the frequency spectrum from samples. You're basically saying you've got a bunch of samples that of these energies that we were multiplying by sinc functions or convolving with sinc functions to give you these, which is the standard way of recreating a signal. And ultimately, you get a bunch of sinc functions in just the right way that give you the original frequency spectrum. So you're reconstructing the frequency spectrum from samples. That's what the Schrodinger equation is doing in the time domain. And you can use this to do the second order calculation too, which is a huge, I think, calculation benefit where you've decoupled the first time variable from the second time variable. It's a nested variable in typical approach, and it's very hard to solve, computationally expensive. Here we're using convolution to do so, and it's, I think, more suited, especially to quantum algorithms, but in general, just more smooth. And just to be clear, at this point, this is where Dyson introduced the time ordering operator, but we don't have to do that. We can use this other method of Fourier transform recursion to decouple the integrals. So thanks a lot for listening, and I can't wait for your questions.